Good afternoon. On behalf of IASTA, I welcome all who have joined us for attending 18th lecture of IASTA monthly online lecture series. I am Manish, Secretary IASTA. So as you know that after its formation in 1988, IASTA continuously promotes exchange of knowledge pertaining to aerosol science and its applications. After starting this lecture series in 2023 and continuing it in 2024, we now move to 2025, and this is the first lecture for this year, and we have been fortunate to get an appropriate topic as well as distinguished speaker for this lecture. Before we move to the lecture, I would like to announce that 14th Asian Aerosol Conference will be taking place between 2 to 5 December in Mumbai. So there are many participants right now in this meeting. So your contribution as a participant in AAC 2025 will be the first step towards its success. I am sure that most of you will write papers for the conference and come to Mumbai. Now, coming back to today's lecture, the lecture focuses on aerosol effects on extreme heat in Indian region, a fascinating aspect. So, tell you more about the speaker, I invite Dr. Subha Verma from IIT Kharagpur. Dr. Subha, please.
Okay, so just a second. Colleagues, I am honored to introduce you one of India's most precious gems in aerosol research. This gem is profoundly and very finely beaded with numerous national and international honors, awards, which includes Fellow of almost all Indian National Academies of Science and Engineering, the World Academy of Sciences, Fulbright Nehru Fellowship, PRL Vikram Sarabhai Award, Teaching and Research Excellence Awards at IIT Bombay, and very recently, the Distinguished Alum Award 2024 from IIT Delhi. This gem sparkles with knowledge of aerosol science and research contributions, authoring over 150 widely cited publications, a book, and 4 patents. So, colleagues, get ready to enrich yourself with the emerging beams of knowledge and science legacy during her lecture. Colleagues, this gem is a pioneer in national aerosol emission inventory development, has a vital role in advancing the area of climate science and air pollution research in India, to policy networks globally, recently as a member of the Science Advisory Panel of Climate and Clean Air Coalition of the UNEP. She has courageously introduced various scientific challenges pertaining to the domain of aerosols and climate with a focus on India-centric problems, as she is doing today as well, while also serving as the national coordinator of a multi-institutional project on National Carbonaceous Aerosol Program. And on my personal front, with a message to all PhD students here, dear students, this gem is also one of the academic creators of myself and Professor Ghazala Habib from IIT Delhi, being our PhD supervisors. And so, living in Bharat nation and in the land of Ramakrishna Paramhans and Swami Vivekananda, I also feel proud introducing her as my Guru Amma. May the Almighty bless this gem to continue sparkling with the brightening beams of knowledge forever and ever through her academic contributions and boundless research energy. So, colleagues, let us join hands in welcoming this sparkling gem of our country, Professor Chandra Venkataraman from the Indian Institute of Technology, Bombay, for the IASTA lecture of today, entitled Aerosols and Extreme Heat, Unforeseen Killings in the Indian Region. Thank you.
Thank you, Professor Shubha. It's indeed a great pleasure to be here. Thank you, colleagues, for attending this lecture. I'm going to try and share my screen now. Is the screen visible?
Yes, ma'am, it is.
Okay, fantastic. So today, on behalf of the Coalesce Network, I'm extremely delighted to share our work on aerosols and extreme heat, unforeseen links in the Indian region. So the National Carbonaceous Aerosols Program was launched, and then we started this project in 2017 with the participation of more than 20 institutions to understand scientific complexities related to carbonaceous aerosols in terms of their origin, which is emissions, fate, and their roles as drivers of regional climate change over India. And as the project proceeded, we also brought in air pollution, particularly climate feedback to air pollution. So this is the work, of course, with contributions from over 85 researchers and 40 plus investigators. And I'm going to try and weave the story about aerosols and extreme heat. So the context is that there is increased heat wave occurrence in South Asia. What is being shown here at the top is, I'm going to try and go to a laser pointer, that we have summertime, which is March, April, May, June, mean temperatures rising consistently from 1960 to 2009. We also have an increase in the number of heat wave days, which is in percentage shown here in different parts of the country. Now, heat wave is something that has a operational definition in terms of a threshold, sometimes defined as greater than 40 degrees centigrade dry heat, which is the daily maximum temperature in the plains, while 37 on the coast. And what's important to understand is that humidity also plays a role. Now, the 2015 heat wave, unfortunately, claimed 2,000 lives in India and 1,500 lives in Pakistan. And what is being shown here is what are called temperature anomalies, which is that year's temperature in different periods, May 21 to 28, May 29 to June 4, etc., and the difference with its long-term mean. So we see that we had very large temperature increases compared to the long-term mean, that a very large region was affected. Now, what's interesting about heat waves and unfortunate is that even a 0.5 degree centigrade increase in temperature or 2 additional heat wave days can cause a very high risk of mass deaths. There's an exponential relationship. And when it's accompanied with high humidity, then the body is unable to perspire and to relieve physiological stress, and that makes it a worse sort of situation. In addition, of course, we have very high air pollution levels. Unfortunately, for all our friends in the Indo-Gangetic Plain, they're experiencing it every day practically for November, December, Jan, and Feb. We've started experiencing quite horrendous air pollution levels in Mumbai. What is being shown here, of course, is these levels being modeled in different ways. 2015 baseline, and these are daily values for recent years using chemical transport models and using AI/ML techniques. So we have the national ambient air quality standard of 40 microgram per meter cube PM 2.5 on an annual basis. But I'd like, of course, to alert all of us to the fact that WHO has a new guideline of 5 microgram per meter cube as a safe level. So we are, looking at very, very large 80 to 150 microgram per meter cubed all over the Indo-Gangetic Plain. For some of us who've been around for a very long time, a historical comment on one of the early studies is Indian Ocean Experiment 1999. And what was studied was the outflow from India onto the Indian Ocean in the northeast monsoon time period, so exactly January, February, March. And there were measurements made in the continent, but also in Maldives at one of the observatories. And one of the big findings was that black carbon had a very significant contribution to the aerosol mass, as shown over here in terms of particular aerosol sizes, and that there was a very large atmospheric heating and a surface cooling component to caused by the aerosols. There was also some investigation about whether or not they arose from fossil fuels or biomass burning. At that time, the only available measurements of biomass burning were open forest fires and some agricultural fires, which have large amounts of organic carbon compared to elemental carbon. On that basis, they concluded that fossil fuel combustion is a major source. But then a few years later, we were able to do very seminal work, which showed that for small fires that are well tended, like the Chula fires, which we had very careful lab experiments made by Ghazala Habib, who's now professor in IIT Delhi, that essentially you could even have half the PM 2.5 mass being black carbon. So that shifted our understanding that biomass can be an important source of absorbing aerosols. But at that point, the focus was all on black carbon. So with this kind of background, we went to coalesce project with the understanding that data sets of short-lived climate forces are highly limited. Important gaps remain. We had secondary data underpinning emission estimates, but we did not have too much primary data. And there was also not very much of an understanding of aerosol intrinsic properties. And so we went to the Coalesce network with a work package on source characterization and emissions, which I will describe, and a second one on a national observational network for source apportionment and to understand atmospheric transformations, and a third one with modeling using GCMs and regional climate models to understand climate and air quality impacts. So if you look at this, there are two approaches. The top-down approach, where measurements are ingested in receptor models to find a top-down source influence, which is very, very common to the air pollution community. And then the second one, which is the bottom-up approach, where emissions are input to climate models. And this is called the bottom-up approach, and this is very, very common to the climate and even some part of air pollution communities, but really to the climate community. So we had an integration of these methods here. So coming first to intrinsic optical properties, the countrywide observational network, again, a first for India to operate from Srinagar to Mysuru, Bikaner to Jorhat. So north, south, and east, west transect. A little bit sparse, that's all the funding we were given. But essentially to make coordinated PM 2.5 measurements. 11 location, alternate days for 2 years with over 50 chemical constituent measurements. To people in other parts of the world, this will not look very interesting because they have network observations of aerosol chemical composition readily available. However, this is the first coherent data set. What is being shown here was that each of these sites was picked to be regionally representative. So the PM 2.5, this was done from using statistical methods on daily PM 2.5 derived from satellite. And what is being shown is that the coefficient of divergence is low of that site compared to its neighboring pixels. The Pearson correlation coefficient is high, saying that there's a covariance with its surrounding areas, and both these being linear relationships, mutual information captured being high, captured possible non-linear relationships between the site and its neighbors. So essentially, these sites were set up to be regionally representative. And so first sort of main result If we look at pink, which is sulfate, purple, which is nitrate, and yellow, which is ammonium, we basically find something different from other world regions in that the ionic constituents, which are the secondary species, are smaller in fraction than the sum of the primary species. So the sum of the primary species is elemental carbon or black carbon, organic aerosol. This is reconstructed dust from the elemental composition. In some cases, there is quite a bit of unexplained mass to the gravimetric value. And so the first takeaway is Indian region aerosols have primary species dominance with quite a large carbonaceous fraction. Could be even up to 15% black carbon and 30% organic matter, which then, gives practically half the PM 2.5 mass as coming from carbonaceous constituents. Talking about optical properties, as we said at the time of before starting this project, there was an understanding that black carbon, of course, is a major atmospheric absorber. And then dust is another contributor. And then there are mixing effects. There are various other effects that can enhance it. Now, over the last 2.5 decades, there's been an understanding that there is brown carbon, which was originally thought to be very weakly absorbing. So if we look at the complex refractive index, N plus IK, N being the real or scattering part, and K being the imaginary or absorbing part, then what was thought was that we have a very low K value, but we have a pretty high W, which is related to the absorbing angstrom exponent. So there's a strong spectral dependence and a low absorption value. Now, over the last 5 to 8 years or so, from 2018 onwards, the work of Rawad Saleh et al., which was done in the laboratory with gaseous fuels burned under very controlled conditions, they showed that you don't just have the very weakly absorbing BRC and the black carbon with very different optical properties, but you in fact have a whole bunch, a series of carbons along the way, which are weakly, moderately, and strongly absorbing organics. And these are then called dark brown carbon by the time they become moderately or strongly absorbing. So this had been shown in the lab. And so we went about to see how absorbing are Indian region aerosols with this kind of understanding that we knew 880 nanometers, and this is all our 11 or not quite 11 sites. I think we had 8 sites over here, 8 or 9. So while the 880 nanometer is telling us about the black carbon absorption, the 410 nanometer is an indication, along with the large values of AAE, which you see in the third bar, of the presence of brown carbon. So significant amounts of brown carbon as well, which is the large absorption at 410 nanometer, as well as angstrom absorption angstrom exponents having large values. The other sort of very interesting thing is the mass absorption cross-section, which is meter square per gram. And what we see here is you have values between 2 and 4, showing that the aerosol is intrinsically very absorbing in nature. Even if you go to Mahabaleshwar, which has 25 microgram per meter cubed, Mysuru, which has about 30 microgram per meter cubed, PM 2.5, the MAC is still of the order of 3. So regardless of whether you have low levels of PM 2.5 or high levels of PM 2.5, the intrinsic nature is quite absorbing. So then we tried to derive the brown carbon absorption fraction from this, and this is done by using spectral optical methods and a me theory based way without constraining the black carbon and AAE to equal. We don't set it equal to 1, but we have an optimization method, and found that in most sites, in most seasons, between 20 to 40% of the absorption, and this is at 410 nanometers, is from brown carbon. In some of the sites, in some of the seasons, you could have even 50 to 70%. So very large amounts of brown carbon absorption. So this is, people have been publishing about brown carbon. We're reiterating their findings that in Indian ambient aerosols, there's quite a bit of brown carbon in addition to the black carbon. And then the question naturally arises, where does the brown carbon come from? Okay, but before that, specifically about the Rohtak site, we had an opportunity to do an intensive field campaign where we were able to have an SMPS, ethylometer, nephelometer, OPC, etc., running for 2 months, and also filter-based samples. So what we find is Rohtak in winter was dominated by a lot of what is called OC3 and OC4. For people who do thermally resolved carbon measurements, these are the more, let's say, refractory fractions of organic carbon, the larger organic carbon molecules, which tend to stay in the particle phase and tend not to photo-bleach much. And what we find is that contributes a large part of the organic carbon. And we also found that there's low single scattering albedo centering around 0.78, which is very, very absorbing, and with reasonable angstrom exponents, which once again is indicating that you have the black carbon, but also organic carbon, brown carbon absorption. And we were able to use what is called a Lorentz-Mean inversion method, which was pioneered by Rajan Chakravarty's group with PyMe-Scat as the software that's available to do that, and show that the imaginary refractive index was in fact larger than previous measurements. And the other thing is the imaginary refractive index is not typically used in climate models for radiative forcing calculations. Organic carbon is essentially treated as a purely scattering species. So this becomes important from a climate modeling point of view as well. Coming to the field campaign, we know that making measurements of emission factors, here we see our students Taveen, Navinya, and Anurag, setting up in the field a dilution sampler that was developed and there's a publication out there, Professor Ghazala Habib's group, and this was essentially used to capture both area sources. Here, Taveen is measuring the plume from agricultural residue burning, and we will see cooking. So you can see this 8-arm sampler to get a good sampling. You could see the 5 filters, ethylometer and nephelometer. Here, Navinya and people were measuring brick kilns. We have Shehzad Khan measuring emissions from a tractor. So when we went to tractors, automobiles, and to brick kilns, we were able to sample directly from the tailpipe. So the sampler can quantitatively make measurements of area sources as well as of stack emissions or point sources. And so with this new and fairly comprehensive data set of regionally measured emission factors, we also had 15 participating institutions work on survey-based data collection, and were able then to build an emission inventory with new methodologies for residential cooking, heating and lighting, agricultural residue burning, fired clay brick production, and on-road transport, which essentially says that this is one of the biggest efforts in terms of primary data sets underpinning the emissions calculations. And we are still working on the user interface, and hopefully we'll have it ready for release at some point. So we have all sectors: energy, industry, transport, residential, agriculture, short-lived climate pollutants, BCOC, methane, SO2, and MVOCs, NOx, air pollutants, primary PM 2.5 CO, and even have CO2 and N2O. So this will be a tool that gives us the emissions on district, state, and national scales, but it is at a 5-kilometer resolution, and we hope to make it go down to city scales too. So what were some of the big findings? Jyoti Kumari from IIT Delhi, her big finding was that despite us having a very, very big and a really great effort through the Pradhan Mantri Ujjwala Yojana to provide LPG, there's only 30% really from survey data of users that are exclusive LPG users. There's unfortunately 40% of the population that solely relies on solid biomass fuels and coal. So solid fuels, highly polluting. And even the 30% that uses a mix is using quite a lot of biomass fuel, 60 to 90% of their energy needs. So we end up being able to estimate the total emissions. Once again, how absorbing are the particles? If we look at elemental carbon, there are 3 blue things here, EC1, 2, and 3. And then there's OC3 and 4, which in this case happen to be light brown. But this continuum over here is the absorbing part of the emissions, which is quite a large fraction of the bar, is what we'd like to show. Seasonality was introduced based on the surveys, based on space heating and water heating needs in winter being higher than summer. So similar to that, looking at agricultural residues then, we have this idea that, the surplus crop residue can be calculated, and this is an internationally used IPCC approved procedure that says you take the crop production, you multiply it by the residue to crop ratio, you have some dry matter fraction and a combustion efficiency. And then a big unknown, a fraction burned, which IPCC tells us to use as 0.25. So based on our detailed surveys and modeling, we're able to show that this can vary anywhere from 0.15 or 0.1 all the way to 0.45 in different districts of India. This is work of Taveen Kapoor. And that while rice and wheat straw form a large part, 2/3, still 1/3 of the emissions are sugarcane, maize, oil seeds, groundnut, cotton, etc. And many of these tend to be stalks and not straws. We have a very strong seasonal distribution with the Rabi and Kharif harvests and the post-harvest burning. And once again, here we're looking at the grays and the browns, a large amount of the absorbing components that are present. So emissions now, and particularly from biomass fuels, contain large amounts of the carbonaceous species, including what would be the brown carbon type of species. Coming to work by Navinya Chimurkar, just hot off the press, few months ago, ACP very, very interestingly, this is one of the first demonstrations of the black carbon, brown carbon absorption continuum in field measurements. So Rawad Saleh and group had shown it in many other in laboratory measurements of gaseous hydrocarbon fuels. But here it's being shown that we have the weakly absorbing brown carbon, the moderately absorbing, and even some strongly absorbing brown carbon, and then the black carbon. From agricultural residue burning, brick production, cooking and heating field experiments. What's interesting here to notice is that some of the agricultural residue burning diamonds and this brick experiment had moderately to strongly absorbing BRC associated with them. A large number of the cooking experiments and heating experiments seem to have lower absorption values, sort of weakly to moderately absorbing over here. What's interesting is that moderately absorbing may be defined as having a W of this nature of 1 to 4, but really we have a lot of points lying here which says that they are moderately absorbing and have higher Ws, which means that at the lower end of the solar spectrum, they are likely to absorb rather strongly. So these are all very, very interesting results here, showing unusual and unforeseen sort of results. And then Navinya developed this parametrization, being able to calculate K, which is the absorbing part of the refractive index of BRC at 550 nanometers, and the wavelength dependence factor W as a fraction of black carbon to organic aerosol in the samples. And then what we could do was be able to ask the question, where are absorbing aerosols emitted from? This is the biomass burning organic carbon emissions in our emissions inventory. He's showing cooking, heating, agricultural residue burning, and others. There was a surprise. We found that the Indo-Gangetic Plain, which is the largest amount of organic aerosol emissions, doesn't have the highest absorbing aerosols because it happens to be cooking related. But indeed, you have the space heating related and the agricultural residue burning related emissions, which have some of the higher values of K. So this is giving you an idea where the most absorbing emissions are coming from. So with these kind of intrinsic aerosol properties, we have absorbing, warming particles, and the intrinsic absorption comes from both black and significant amounts of brown carbon. We have the emissions inventory, which was then utilized in climate and air quality simulations. So for people who run WRF-Chem, this will make sense to you. We actually found that we had later on made a somewhat unfortunate selection of chemistry scheme with radon-2 made sorghum, which didn't give us it gave us erroneously too low secondary organic aerosols. But, some of the things you learn only by experience, and it's very important to evaluate chemical schemes before you go ahead and work with them. So, nevertheless, given the fact that even the observation showed primary as a significant component, we ran a simulation for a whole year, and these are all the emissions being shown, which is basically saying that residential and agriculture dominates, organic carbon, large part of black carbon, and NMVOC emissions. But this is purple is industry and energy, Industry, energy, and transport dominate the SO2 and NOx emissions. There is some seasonality. And after we run the simulations, then it gives tweaking the model. Arushi Sharma and Kaushik Muduchuru did a lot of work in getting the model to work right. And at the end of the day, then we're able to close an annual mean NMB reasonably well. So then we can ask the model. This is the ongoing work of Sujit Maji, who is at IIT Pune. We can ask the model, what is the fractional contribution of the residential sector? So you would have a pair of simulations, one with all emissions turned on and one with only residential turned off, and the difference between them giving the residential contribution. And we're looking at it in November, December, January, February, where the heating and the space and water heating needs are the most. And what we find is black carbon, organic aerosol, and PM 2.5, particularly in North India and some parts of Northeast India, very, very large amounts of the concentrations arise from the residential sector. And the details are given here in terms of actual numbers. We can ask the same question of agricultural residue burning. And there are two very, very interesting takeaways. Agricultural residue burning is considered to be only affecting the northern plains and really in October, November. But as we find, there is significant burning in December, January, February, and in March, April, May, and also in central India and northeast India. So we need really to look at agricultural emissions, not just from the view of the Kharif emissions, but also the early Rabi and the late Rabi emissions. And we can see that there is, a significant effect, anywhere 10 to 30% of the emissions, but still the concentrations are very high. So the overall takeaway is biomass, fuel, and open burning emissions are strongly contributing across airsheds. So if you take our simulation output and you say, hey, I'm going to divide India into 0 to 40 microgram per meter cube, 40 to 80, and then 80 to as high as it goes, and have 3 divisions here, and ask what are the sources impacting PM 2.5 in these 3 divisions, you will see that a large amount of the sources are still yellow and green in the cleanest regions as well as in the dirtiest regions. So what we're saying is that biomass as a source of emissions, whether it is small fires for cooking, heating, whether it is large fires for agricultural residue burning, waste burning, is a pretty strong contributor to emissions throughout India. So with this idea, we then move on to, I will try to now speed up and finish up in about a few minutes, but this is the climate connection. So when we look at regional warming, the question we're asking is, we have global warming, but global warming, despite all of us using global mean radiative forcing and all as metrics, it is spatially heterogeneous. And so regional changes can be because of regional dynamic changes. There can be some changes in regional circulation, could bring in wind from warmer regions, could bring in winds with certain types of pollutants, as we'll find. And then there is the thermodynamic component. And the thermodynamic component is the surface energy balance. How does it alter sensible and latent heat fluxes? What does it do to the energy balance at the surface? And therefore, what is the surface temperature response? In most world regions, scattering aerosols predominate. So all over North America, Europe, Australia, etc., except for the fire season now, The aerosols are largely sulfate, nitrate, organic carbon, purely scattering components, and their influence is a cooling of the surface temperature. However, we did a very nice analysis. Prashant Dave, who worked with us, did an analysis using absorbing aerosol index, satellite-derived proxy for absorbing aerosols, and looked at a 35-year data set from 1979 to 2013, and also at the daily maxima. So one of the problems that has sort of let us say, plagued this idea of whether black carbon is really contributing to global warming or not is the idea that everybody is looking at annual mean temperature responses or annual or even at best summertime mean temperature responses. But really heat waves are defined in terms of the T max, the maximum temperature that occurs and or the maximum wet bulb temperature that occurs. So what he did was he looked at Tmax during March, April, May, June, and in Northwest India, and he found it increasing. And he found that doing a cross correlation between Tmax with absorbing aerosol index, every pixel versus every other pixel, it had a positive correlation with local absorbing aerosols, which is Northwest Tmax to Northwest AAI, but it also had, very interestingly, a relationship of Northwest Tmax to Central India AAI. And this is something which we have not yet resolved. So if someone's looking for a hypothesis, here it is, which is why does Central India absorbing aerosols cause a spike in Northwest India temperature maxima during March, April, May, June. But let's notice, okay, let's go on to the fact that we didn't stop with correlation. He was very gifted in mathematical methods and statistics. Our collaborator, Mani Bhushan, was his main advisor, and he did a Granger causality analysis, which showed that the absorbing aerosol index went up. This is a daily value. And with a lag, the Tmax followed. And it followed with a lag of 3 days, sometimes 1 day, sometimes 5 days, sometimes. But you can see that there is a lead lag relationship between the absorbing aerosols going up and then the maximum temperature rising. So this he showed for many years, and he showed the causality to hold for 11 of the 35 years, the local effect, and 9 of the 35 years, non-local effect. So aerosols in India are related not with a cooling of surface temperatures, but a significant intensification of Tmax, and by very, very large amounts, 0.1 to 1.6 degrees centigrade on daily scales. We then wanted to query a model, which is WRF-Chem again. This is Arushi Sharma's work, collaborating with Devashish and Manish. And basically setting the context here, this 2015 heat wave claimed 2,000 lives in India. And this is the absolute single largest value annually so far, before 2015 and after 2015. This is showing the AAI anomaly over this big region where the heat wave occurred. And it's also showing that the temperature maxima anomaly, and this is once again during May and June when that heat wave occurred, it's a positive value in terms of the degrees increase per year from 1980 to 2015, as well as the AAI anomaly is also going up. So we can see these as sort of observational evidence. And then we had a pair of simulations with and without the aerosol radiative interaction, the ARI, which people know who are modelers, that WRF-Chem has a switch to turn on and off the aerosol radiative interaction. We called it warming aerosol effect to make people understand the aerosol radiative effect in the region, even though it includes scatterers like organic carbon, sulfate, nitrate, ammonium, etc., the net is a warming effect. And in the model, I have to confess that organic carbon is purely scattering. We only have black carbon and dust as absorbing species. But what Arushi found was, if you look at the model when it's run with the aerosol radiative interaction, red, minus without, which is blue. And in this case, the aerosol cloud interaction was retained unaltered. Then the direct radiative effect on a daily basis caused the T max to increase anywhere from 0.2 to 1 degree centigrade from 23 May to 5 June in the model, which coincided with some of the heat wave observational studies. And interestingly enough, in June 6th to June 29th, the wet bulb temperature, which accounts for relative humidity as well, and we find very large differences between red and blue, which is with the aerosol radiative effect. So the aerosol radiative effect is driving up daily temperature maxima of dry heat stress as well as moist heat stress. And we have now the underlying mechanism as well. So here this is depicted again that spatially, that this is the region, this is the increase in daily maximum temperature. And what really happened was, if you look at kernel probability density functions, looking at each pixel and then plotting it up like this, then we have the probability of T max being higher at higher, shifting to the right, larger temperatures, higher probability. And this is black carbon concentration. So it was coincident with an increase in black carbon concentration in the region. So then we asked the question, what induced the shift or the increase in the black carbon concentrations, and what was the underlying entire effect? I'm going to set off a animation here. Oh, okay. So I think I have to get out of the pointer to set off the animation. And what we're seeing is that the black carbon is actually flowing in from the north. The wind is bringing it in from the north, northwest. I'll set it off again. And we have north, northwest, large black carbon coming in. And the daily black carbon between a difference of the simulations is a positive in microgram per meter cubed. So this is really the dynamic change. The winds changed and brought in black carbon. And what was the thermodynamic effect? Lower tropospheric stability increased, so the black carbon was pressed close to the ground. The net surface shortwave flux increased, and therefore shortwave was being trapped in the surface atmospheric layer. And that led to the dry bulb maximum temperature increases. So now we have a mix of the dynamic and thermodynamic effect. And if we then go on to the wet bulb temperature story for the period June 8 to 29, same kind of thing over here with wet bulb temperatures being larger. What really changed was that larger WBT and in fact greater frequency of occurrence. And what changed was surface layer relative humidity. There was a greater frequency of occurrence of higher relative humidities in the surface layer. And if we want to look at the whole, let's say, mechanism here, we have the dynamic effect. If you look here carefully, the moisture is coming in from the north in the first half, but then it's coming up from the south in the second half of the period. So you can see these two different moisture peaks here. And if we set off the animation again, The dynamic effect is moisture coming in from the northwest in the first half, this peak, and the second half, it's coming in from the south. And again, lower tropospheric stabilities increase, the moisture pressed close to the ground, and the wet bulk temperature goes up. So, we have now an understanding that it's a combination of the dynamic and the thermodynamic effect. If you want to ask, how much did the aerosol radiative effect worsen population and land exposure? You can basically take a difference between the two simulations and say how much more land was affected and how many more people were affected. This is shown for dry heat stress and moist heat stress. About 200,000 square kilometers more of land and 30 million more persons were exposed to extreme heat, Tmax greater than 40 and WBT greater than 25 degrees centigrade because of the aerosol effect. So this is basically telling us that air pollution is worsening temperature extremes and heat waves in terms of their intensity over India, and that reducing air pollution can give us a way also through focus on short-lived climate pollutants like black carbon and the brown carbons to control our temperature trajectory. So yes, I will leave these conclusions up. Basically that, we have a lot of warming nature of particles. There's evidence that aerosol levels are linked to worsening. And we hope collaboratively to have many more people participating in the exciting science in further unraveling these links between air pollution and climate change and finding effective strategies for mitigation. Thank you.
Thank you. Thank you so much, Mr. Venkataraman. It was such a wonderful, informative talk. And I'm sure there will be many, many questions. So what I would request to the audience that please raise your hand. And I will, if you can ask directly, means I will allow you to ask. Otherwise, you can type the question in the chat box. So, yeah, anybody would like to ask the question? Or meanwhile, I will. Professor Abhijit Chatterjee, you have written something in the chat box. You want to ask directly, or should I read the question?
Yeah,
Please go ahead. Please, Abhijit, please go ahead.
Okay, thank you, ma'am. It's a nice talk. This is Professor Abhijit here from Bosch Institute. So, hello, ma'am. Can you hear me?
I can hear you. Yeah, hi.
Yeah, hi. My question was that based on the slide number 29, yeah, this one, that you talked about that transport of maybe the absorbing aerosol from the northwest India to central India, and yeah, or the correlations between these AAI and the Tmax. So my question is, how, I mean, while correlating these correlation, I mean, between AAI and Tmax, how the land use land cover changes be normalized? I mean, is that possible that land use land cover changes are playing a major role over the types of aerosols absorbing or whatever? That is actually playing the role for these temperature extremes or something, and not the aerosols. I mean, how these land use land cover changes have been taken into account. That's my question.
Okay. So thanks, Abhijit. Interesting question. Let me first kind of make a couple of comments that over here, this is a statistical analysis. And so what it is saying is with a lead of, anywhere from 1 to 5 days, increases in daily mean AAI in central India led to driving up the temperature Tmax in northern India, right? So we're not talking about transport of particles at all, right? We're talking really about somehow when you have absorbing aerosols and you're adding heat to the atmospheric layer, there has to be, the heat has to go somewhere. So it's really thermal diffusion. What is happening, how it's getting transported is an open question. In regard to your question regarding land use, land cover, etc., there are several studies that are trying to look at the irrigation effect on changes in a surface temperature. It was considered to be a cooling effect with a lot of irrigation in India, but then they found the models were overdoing the cooling effect. As far as our modeling study goes, which is Arushi Sharma's work that I shared, there is a land use, land cover scheme in WRF-Chem, which is left unchanged between the two simulations. So essentially, sure, if you have land use, land cover changes that can change the surface radiative energy balance, sensible heat, and also latent heat, etc. But in this particular case, we isolated the aerosol effect. The land use, land cover is dealt with in identical ways in the pair of simulations. Is that useful?
Yeah, thank you. Thank you, ma'am.
Okay.
Okay, another question, Dr. Dev Prashad, you would like to ask directly? Or let me read his question. So what's the reason for lower imaginary effective index over the IGP? Does it have any seasonality? And how about this in crop residuability plate? So 3 questions merged here together. So,
Yeah. Now, obviously there's linkages. So yeah. So we unfortunately were able to do this study of an intensive observational study only at one location and only in that period, which was January and February. And therefore, I can try to answer, I mean, imaginary refractive index is derived from the spectral absorption, right? So I can try to answer your seasonality and your spatial difference from Taveen Kapoor's paper in GRL, which is the one that I showed you, which has the let me see if I can get to it, which has the sites showing the absorption. So if we're looking at the site showing the absorption, I mean, one doesn't have to necessarily derive refractive index. You can look at things like the absorption, spectral absorption, the MAC, the AAE, and try to make some conclusions. This paper does report some seasonality, Taveen's paper. It is there in GRL 2024. I've cited it here. And the lower refractive index and the absorbing nature is obviously something is related to the emission aerosol. It can be related to the mixing state. And one of the things that's always talked about is absorption enhancement by in a core shell model of aerosol optics. In the old days, the core used to be absorbing and the shell used to be purely scattering. But nowadays, they go to also what's called gray shell. So because you can have absorbing organic carbon, so you visualize the black carbon as a core and the absorption being enhanced by a shell. But you also have non-spherical particle effects and mixing between, let's say, black carbon and the fractal effect as well. So the particle shape effect is very important, and a mixing between fractals and dust is relatively less explored. So really, there's a lot of very interesting things that you can do to try and get more insight into this question. I don't remember the seasonality figure right now off the top of my head from Taveen's paper, but you can look at it and see how the seasonality varied across the sites. He has seasonality for 4 sites.
Let me add one question on this side only.
Yeah.
So here 2 sites you showed is Bhopal and this KMR. I don't know what the derivation for this KMR.
Kashmir, Srinagar.
Yeah, so Kashmir and Bhopal, it is close to 4, this mass absorption cross section. Whereas if you see this Hyderabad and this SHY, I don't know when it's, this is less than 2.
It's
So
Shamnagar.
this, yeah, so this is, yeah, Kolkata. So that means Kolkata, Hyderabad means you are having less than 2, and Kashmir and Bhopal, it is 4. Factor of 2 difference. So what do you think, Mr. What would be the reason for this kind of difference?
So
mean-
what, I mean, it was based on the months in which the measurements were made. Kashmir, we believe, is impacted by space heating quite a lot. And so, you know, there's the source is not very well characterized, not even in our measurements. And Bhopal, what we understood was that there was quite a large amount of agricultural residue burning in the vicinity at the time, is what Professor Sundaraman's group reported to us, Professor Ramya's group. So we can try to explain it from a source perspective, but you know, there's a lot of interesting physics out there. And if to fully answer such a question, one would have to do an intensive study that also does imaging, as well as, you know, ways of being able to derive the shape, and with maybe EDX, the composition of the aerosol side by side. So you'll have to have a real-time EDX and some kind of way to derive a shape also to be able to bring all of that into the optical modeling.
Okay. Can I also ask some questions? If they are not questions, actually, they are more of clarifications. Can you go to slide 9, just 2 slides before, where you were showing the composition? Yeah. Yes, slide 9.
Yeah.
Yes, it's here. So here, if you see again, means Mysuru, Hyderabad, Kolkata, and Rohtak. So unexplained mass, that is quite large compared to if you see other. So means what I was trying to understand here, whether it is the number of species uniform means for all the sites equal number of species, or because of that difference you are getting this.
No. So for all the sites, in fact, the chemical analysis was done by 4 institutes only. IISER Bhopal handled Mysuru, Bhopal, and oh my God, and Mishra. IIT Bombay handled Mahabaleshwar, Hyderabad, and Rohtak, and IIT Delhi handled Mohali, Kashmir, Bikaner, while IIT Kanpur handled Jorhat and something else, Shamnagar. So basically, Professor Ramya, you know, these are data that were at some level of cleanliness and they have been cleaned up further. So we will have an updated slide of being able to correct the unexplained mass. But there was the full OCEC, all the ions.
Yeah, I saw at the bottom you have written what are the species.
Yeah,
so I see dust is already there.
No, the full dust means basically the entire EDXRF. And so the dust is really reconstructed dust from using this, you know, Chow et al. Type of formula.
Why I asked this question, if you see all this right-hand side, so all these have higher unidentified fraction. So is it related to something, different type of aerosols are there which we are not able to identify with the available measurements?
I see. So I mean, all I can say is no, that doesn't seem to be the case. That doesn't seem to be the case. We just have to look very carefully at at the measurements again and see if indeed the unexplained mass is that large or not.
Another clarification is slide 12.
Yeah.
So for slide 12, just to after two slides. Yeah. Next, yeah, here. So here you have used this for brown carbon, you have used 410 nanometer. You have done. Usually people use 370 or 365. For accelerometer, people use 370. So is there any particular reason you are using 410?
So these are not accelerometer measurements. These are taking a Teflon filter and then doing an absorption measurement using an integrated absorption measurement. They were done collaboratively with Rajan Chakravarti's lab. And the reason to do that is to avoid the matrix effects of these thick filters. So it's a method that was developed by them for optically thin substrates. And so this was done by Teflon substrates. So that is why we had the measurement being made at different wavelengths than what you get from a typical multi-wavelength accelerometer.
And my last question is slide 19, if you can go to 19.
Yeah.
Yeah. So when we do sampling, so sometimes if we are very close to the source, so either means if you are if you want to characterize the source, so we don't allow any other ambient air to mix, so that whatever you are collecting is all from that source only. Or we do slightly away so that it is well mixed with other things, and then whatever you are collecting, that is the sample. But this kind of is where I see this inlet is close to the source. So it is inhomogeneous kind of mixing. So sometimes you may be collecting too much of from the source, or sometimes ambient air contribution will be there.
So, I would encourage people to look into what is called the carbon balance method. It is a quantitative way to estimate the emissions from a plume by looking at the differences in CO2 levels between the plume and the background, and taking a ratio of all other pollutants to the CO2. So it's a quantitative measurement.
While collecting, you have some other measurement also.
We have tons of other measurements
which were making sure that you are collecting the plume from the source.
Yeah, that allows us to sort of isolate what is in the plume from what is, a background.
So now I see another question.
Yeah, I see somebody who says, can you share 2 or 3 main takeaway pointers? So you see, I suppose the unresolved ideas for other people to kind of think about is, of course, really try and understand brown carbon absorption or absorption that's not exerted by black carbon, whether it's brown carbon, whether it's mixing of species, and so on and so forth. So that is, a whole set of things that people can look at. There are a lot of interesting things which I didn't show, which are interesting takeaways for the National Clean Air Program. From the new emission inventory, we find that if you take the 131 NCAP non-attainment cities, and we can ask the question, what is the emission from the city? What is the emission from rest of India? So you see, in Maharashtra, for example, emissions of primary PM 2.5 from the 18 or 19 non-attainment cities is 10% of Maharashtra's primary PM 2.5. SO2 and NOx are 30%. So there's a lot of emissions that lies outside the city. So one of the big takeaways, and if you go to states like Uttar Pradesh, it's not 17% and 30, not 7%, 17% and 30%, it's 4%. So a large amount of the emissions lie outside of the cities, and having only city-centric kind of strategies, how do we expand them to make them more effective? What combination of city plus state air pollution controls will be effective for helping us achieve air quality standards? So that's another thing for people to think about. And then, of course, I think I didn't present much of the data, but looking at the aerosol effects on other climate variables, precipitation, etc.
Okay, now you see people are adding more questions.
Yeah, no, that's
So-
fine. So, Deva Prasad, did you calculate radiative forcing? No, because we don't run a model that, can be modified, but hopefully we will be doing that collaboratively, which is, you see, you need to be able to take a GCM or a regional climate model and go into the optical properties file and insert into it the optical properties in whichever way the model uses it, whether the model uses it as an imaginary refractive index. If you use the values in the papers for organic carbon, you don't use purely scattering, and you use the values in the papers for the organic carbon, then you should be able to calculate the radiative forcing from brown carbon. That's how it has to be done. We haven't yet done it.
And another question I think is not very clear.
It says, is there any effect of aerosols during winter? Yes, of course, the concentrations, so the effects on air pollution. Oh, maybe she was asking about heat. Is there an effect of aerosols during winter? So Aditi, is that what yes, okay, that's what she was asking. We do know that having a large amount of aerosols does lead to being able to confine relative humidity in the surface layer. Whether or not the whole thing can lead to much greater stagnation levels and the development of cold wave type of conditions has to be seen. Right. For example, we have lousy air quality in Mumbai nowadays. And it seems to be some, stagnation levels that are persisting all over northern and central India. And somehow there is the northeast transport, which is with a lot of stagnation during the daytime. So we have slightly better air quality at night, which is very, very surprising because you always expect stagnation at night and not during the day. So some strange things are happening in winter, which we don't understand. Yeah.
Okay, I think there are no more questions.
Okay.
So we come to the last part of this series, which is vote of thanks. Sorry, just a second. Okay. So on behalf of IASTA, first of all, I wish to thank Mr. Chandra Venkataraman for accepting our request. And she readily agreed to give this talk. It's a wonderful talk. Thank you, ma'am. And then we also would like to thank Dr. Shubha Verma for introducing the speaker. Thank you, Dr. Shubha. Then we wish to thank the team who is doing the work in the lecture, mainly DRC team. So thank you. And most importantly, I would like to thank all the students and other people in the audience. Since you are here, so we are trying to bring more and more lecture to bring again. So please follow us on different social media platform on X or LinkedIn or YouTube, and we will be keep giving different information. So with this, I wish to thank you all again. Thank you very much.
Thank you.
Thank you. Thank you very much. Thank you for
Thank you.
facilitating. I enjoyed the discussion very much. Thank you.
Thank you.
Thank you.
Okay, we can close the.